Hello, my name's Duncan McGregor. I'm a former petroleum geologist, worked extensively on Africa, and I realized, come to the end of my career and really realized that, particularly with involvement in conferences and things, that I could occupy my time usefully by putting together this large geological atlas. And you will see essentially the URL for it here. I would encourage you all to look at it. This presentation, I shall be talking only about the paleotectonic maps. As you can see, there's several others: paleogeographic, geothermal gradients, and heat flow maps, integrated tectonic element maps. Some of these I'm still working on. In fact, all of them I'm still working on. But I've reached the state of maturity on the tectonic maps that I can really give this presentation. I really want feedback. So you'll see on the website, you can do this or email me, of course, but you can actually put feedback. I want to know what doing this rubbish. Before we move on, I would acknowledge that the plate tectonic model that this is put together is that of my colleague, Colin Reeves. Again, I'm diehard of a lot of these conferences. So why the study? Well, perhaps the most obvious thing is it doesn't exist. It exists for other continents, particularly Europe. Ziegler and Derkort does not, and Middle East as well, but it does not exist for Africa. It's another reason why to do it is because perhaps Africa, more than any other continent, presents an ideal setting for the large-scale study of basin and margin evolution, particularly extensional tectonics, in that we've got margins of all types and all ages, rifts of multiple ages, types, and different origins, some of which we can still see developing in different stages of development in different areas. And we've got relatively minor compression that would obscure this, so we can see the original extensional fabrics. But we have got these mild transpressional events that tell us a lot of how stress can actually be transmitted across tectonics. Like I say, I'm a petroleum geologist. Part of the reason this study's not been done before is because outcrop geology, except places like Algeria and Libya, Morocco, is generally poor, partly because of the lack of compression, but also because of the current climate and soils types of Africa. And so we do need to actually drill to actually see a lot of the tectonics. Much of this data from the oil industry is coming out pretty slowly and often informally, not peer-reviewed papers. And that is an important component of this talk here. Things like PowerPoint presentations and even scribbles being made at conferences like these Petroleum Exploration Society of Great Britain and Houston Geological Society Africa conferences, which I've been at about or helped organize about 20 of. So the legend for the maps, at least for the paleotectonic maps, the main things to look for are the limits of other plates with this hash diagram. This railway sign for the spreading ridges, quite difficult to see when they first form. Subduction zones, relatively minor. You see them on the northern side. Limits of true oceanic crust. That essentially means the layered volcanics. And they are generally much further out in the basin than previous documents, previous papers have suggested. And that is due to really new seismic. Again, not terribly well published, but you know, reported on. You see a lot of these red lines. The solid ones are the main stages of extensional faulting, and the dashed lines are more minor stages. The less of these purple brown crosses, which are compressional folding and faults, which are put together, and they can be anywhere from a large overthrust to a relatively minor inversion structure, concentrated in the north of the continent. And then the ones that we know about, the major transforms, dextral, if we know they are, sinistral, if not, if we know they are sinistral, and quite a few of these speculative ones that are necessary, but we don't know exactly where they're going. They're necessary to actually transmit transgression to through the continent and create these inversion structures here. And then the volcanics, of course. We show a definition of topography, which is very much derived from apatite studies. And this is a category taken directly from the papers. And also sinks, large sinks of sediment are an indicator in the presence of a wet climate of high topography. As is the paleofacies that we do show on these maps, again, because they provide a pretty useful control. The carbonates obviously suggest it's flat. At the time, the clastics, if it's a wet climate, would suggest that there is some topography around, which would indicate that there's something going on, tectonically. And finally, I mean, I would indicate this is just deep water. You have to go to this line to get to the edge of the plates, which will be within the deep water polygon. So this is just a quick run through of a lot of the diagrams. You see things starting down here on the Permian, gradually moving up to the northern margins with the opening of these northern and northwestern margins, and eventually this eastern margin through here. And we see that that will actually come round, propagate as a smile right all the way up here, eventually through West Africa, and then eventually round here to actually eventually distinguish Africa as a plate in the late Cretaceous. And eventually then South America will drift away, as do the other continents, very quickly. And then things are really well concentrated up here during the Tertiary, all together with the formation of this topography, which is the basin and swell structure of Africa. So that can be looked at your leisure. Now let's go into the type of margins. We have three major types of margins. They are a spectrum between these three. None of them is purely one of the other. The most commonly perceived form of margin are these rifted hyperextended margins, which are typified by Angola here. When it starts as rifts, the rifts come gradually quite hyperextended with lower crustal thinning going on, sag setting in, and then breakthrough of eventually the lower crust, and in cases the actual mantle to surface, before as the asthenosphere rises and eventually leads to the formation of an oceanic ridge after a period of something like 30 million years after the rifting starts. Very well documented here, less well documented through here. We still are debating as to whether there is elements of a volcanic margin here, because there certainly is on the conjugate margin in North America, bits of North Africa, only slight bits. Again, these are oblique to transforms here, where we see this height developing today in the Red Sea, where we have mantle exhumation very recently, and down through East Africa as well. So that makes about just under half of African margins, which might surprise you because this is the most commonly conceived form of margin. The next in line with about a third of margins is the transforms. So what distinguishes a transform is that the spreading ridge comes in oblique or perpendicular to the continental margin, which gives a very sharp transition from continental to oceanic crust, often associated with inversions, as in this example here in Ghana. Now, again, this is the best documented area in here, often called the transform margin, though in fact it does vary quite a bit, bits of hyperextension in there as well. I am proposing in this paper that nearly all of North Africa is in this category in the Jurassic when it forms. And to some extent, that is a new perception, at least for some of you. It's pretty well established in the oil industry. East Africa, again, pretty well known, and the Agulhas margin, which we'll look at in a bit, again, there as well. And all of these we see inversions associated with later change of stresses. Right, so this is perhaps the least understood and perhaps the oldest of these margins, at least in part. It appears to propagate in the Triassic of Lebanon to eventually to the Alpine Ocean in the Middle Jurassic. And so I think most of this in between is early Jurassic through to earliest Middle Jurassic. And it is sort of forming a sort of smile-like pattern again and taking Adria and the Madares Torres off in this direction so that they can be brought in again in the Tertiary to their current position with subduction of this Jurassic Ocean. Now, most of the literature would actually tell you that this is a Permian Ocean, although there is deep water facies in here that have to be explained. There's nearly nothing about the geology in here that we've picked up from oil and gas exploration that would indicate there's anything significant happening in the Permian at all. Indeed, lots of evidence has been seen that this is a Jurassic margin. It starts with Triassic, early Jurassic rifts in here. There are volcanics, both in the onshore and offshore, in the late Triassic, early Jurassic, and also in the Middle Jurassic here, which are flood basalts. Flood basalts are thought not to be associated with the opening. And we have seismic in the Eratosthenes Plateau and in the Kyrenaica wells that indicate a big unconformity of latest early mid-Jurassic age. So they interpret that as a breakup unconformity. Now, the trend of rifting through here looking at Majosian, would tell us that there has to be a big transform along this margin. In fact, there is one quite known well transform here in the Sinai Ranch, and it has been shown on a few seismic lines, but and again alluded to on the many papers, but there's yet to be a dedicated paper showing that transform along the margin. That's something we eagerly await. What's happening in here, I think, is very much dependent on an E&I paper indicating what the stress direction was at that time, suggesting the Ionian Sea had that trajectory, whereas the Eastern Mediterranean, based on the rifting, has to have this trajectory. So things have to swing round and has to be a transform in between. And things, again, as I suggested, are actually propagating in this direction. And the spreading may not last long, perhaps into the early Jurassic, early Cretaceous. Rather more simply and conventionally is the Central Atlantic, which we have adequate, very well documented rifting in the late Triassic, down as far as Senegal. And that leads to spreading in the early Jurassic, which is evidence, slow spreading, as we said. This is evidenced by pillow lavas in the Canaries. But it only gets as far as the Blake Spur, where there is a jump in the limit of oceanic crust. So something has to be happening there. But we know now from work in Guyana, which actually is a Central Atlantic margin, that the oceanic crust eventually was seaward dipping reflectors of Middle Jurassic age, and eventually actual oceanic crust was not in place until the late Jurassic in that area. So this eventually leading through into the Proto-Caribbean and the Gulf of Mexico, where we have oceanic crust of roughly that age. So there's a big leap over the Blake transform sometime in the late mid or early late Jurassic. Things stall for a long time at this transform, which is again something we'll see in West Africa and other margins as well. The whole of one ocean does not need to be the same age. It generally propagates in one direction. Again, this is true in the Indian Ocean. And here we see propagation not only of the rifting from north to south, but also of transgression. This is, again, you see the Pleistocene transgression. The Toarcian transgression goes right down to where the salt here in the Angotchi, as does this Majosian transgression with carbonate platforms bounding deep water on each side, suggesting we have oceanic crust in there. This starts as an oblique margin from we know from the magnetic anomalies, and then takes a shunt and goes into the essentially northeast-west spreading, and then the formation of this Davy and also associated fracture zones such as the Sea Gap in the latest Jurassic. So this is obviously taking Madagascar off to basically its current positions, and then we'll lose India and the Seychelles from that. But I won't go into that. One thing we do mention is that it's dextral movement on these transforms up to the Santonian, and then there is much slower and much less significant sinistral reversal from the Santonian onwards, creating smaller scale inversions. Moving around to South Africa, the conventional interpretation is that this fault, the Agulhas, which forms the continental ocean boundary, got going in earliest Cretaceous, opening a very small part of the southern South Atlantic at that time. I believe it's actually older, the fault. Essentially, we have evidence for large inverted Jurassic basins parallel to the fault, and also extension oblique to it going right here in South Africa and also up here into Mozambique. These rifts have to have an origin of some sort, and I'm proposing that they're passive rifts opened by the first movement of the transform. That is also supported by the paleogeography. We know that this East Falklands Basin is in deep water at the time. That fixes the position of the Falklands because we don't have marine strata in the West Falklands Basin until the Triassic. So this Equans Falklands Basin has to be juxtaposing against these basins in the mid to late Jurassic. Now, the first marine strata go into the Chamtus Basin, and rather later we get marine strata in the Bredasdorp Basin, which suggests to me that the fault is moving and bringing marine strata progressively into western basins in the late Jurassic. It may be that it's this transform that's moving rather than this one, but there certainly is something happening in the late Jurassic before we start opening the South Atlantic, which is what's shown in this slide. Essentially, as we saw, it's just essentially this area up to the Cape transform opens first, then it will go up to roughly in the Otarivian up to the Walvis Bay transform, and then by the Aptian it's up to the Rio Grande Ridge. So this is a volcanic margin in here. Essentially, volcanism continues on the Rio Grande Ridge for some times, which allows the ocean to stop there. And actually, we have a basin formed below sea level in which all these very odd early Aptian non-marine carbonates indicative of a highly alkaline lake form. That eventually seems to get breached in the late Aptian. And again, the evidence for this propagating northwards roughly around the time of salt deposition. Because what's PowerPoint presentations, and it is no more than this, I'm afraid, because they don't show the seismic concern, do show varying geometries, describe different geometries of salt relating to oceanic crust. Salt actually onlapping oceanic crust down here, and salt well removed from an oceanic crust up here. This suggests that this is perhaps mid to late Aptian spreading, latest Aptian to early Albian spreading up here. So again, it really seems to be a propagation rather than a single age. This around the time of late Aptian salt distribution. It initially rifts up here in the Ronkonkwo to Kano Basin, setting up these transforms in here, gives up on that and jumps over here, which is something we see very often in Africa. An attempt to rift somewhere which doesn't succeed, and then it jumps over to actually give later rifts and a spreading center in another location. And eventually, very rapidly up through the Albion, it goes up through here, sets off these transforms in here, which we'll talk about a bit, because there already is transforms in place from other activity. And by the earliest Cenomanian, we have communication between the South Atlantic and the Central Atlantic, which sets off things like contorite currents and contorites, which we don't see until that time. So that's margins in a summary. Now rifts, essentially the classic view of rifts that you'll see in sort of school textbooks is that we have a mantle plume head, the rise of the asthenosphere, extension due to stretching, a large area of topographic uplift, and frequent volcanism derived from the mantle due to the rise of the asthenosphere. And that's characterized really by the East African rift system, very high rift shoulders, and at least in the eastern branch, a lot of volcanics. The other form of rifting, which actually is quite common in Africa, is that associated with major transforms across the continent. You see two types. One's narrow basins, which are frequently very steep and frequently later inverted along the transform, which the correct term would be a releasing bend. I call them transtensional basins. And then passive rifts, which are ones which are pooled open oblique or perpendicular to the transform in either side of the rift. Now we see this multiple times, I believe, in Africa at different times. But the best demonstrated example is in the Cretaceous, associated with the Central African lineament, where we see these transtensional, highly inverted basins along the transform, and then these basins which show very little inversion, very dip-slip tectonics, which are perpendicular or oblique to it, such as these Sudanese basins, which are then Sudan rifts. But we do need a lot more in the way of transforms to actually explain some of these basins, e.g. in Niger. Only has to be another transform coming through here, which is the Trans-African lineament. Again, very highly inverted, probably basins along the transform in this Benue Trough complex of Nigeria. Now, there's numerous populations of rift. In fact, there's rifts on all the time slices, all 19 of the time slices that I've mapped. So we go back to perhaps the oldest are these Permian rifts, and these I see as corresponding very well to that model you saw on the previous slide. In other words, this one, with essentially narrow, very steep half grabens inverted along the transform and dip slit rifts perpendicular to it. Now, the origin of this transform, which is the Southern Trans-African Shear System, documented in a number of papers, I believe probably can be traced into the Cape Fold Belt through these Namibian rifts here. Where it actually hits is probably somewhere in the offshore and is very highly obscured. And it probably is driven by the activity of the Cape Fold Belt itself. When we get into the Trias, the rifting becomes commoner in the northeastern basins. There seems to be a propagation in this direction, which again is a trend. Rifts often propagate as well, and nothing shows that's better than the East African rift system. Now, the poorest understood rifts, I think, are probably these ones, the WD equals Western Desert of Egypt. There's lots of papers and oil company papers in them, but they mention they're transtensional, but very few seismic lines shown. So where is the evidence for it? So do we access this verbatim? The one thing I would say from the regional timing of them is that they do seem to tie well to when we think this transform is moving along the Egyptian margin, when the spreading was actually occurring of the Eastern Mediterranean basin, which we think starts around mid-Jurassic and ends perhaps in early Cretaceous. And actually, these rifts are probably rifting the most in the early Cretaceous. The first rifts are really in Triassic in age, and they support this ocean being early Jurassic or middle Jurassic, and then they seem to sort of propagate into the Western desert. Perhaps there is a movement of this Trans-African lineament again, but also this another one lineament that's proposed is this one through the Alamein Basin, and there's our better documented ones in Kyrenaica. But there probably is a whole series of these lineaments running parallel or oblique to this large one off Egypt, with the model being perhaps the relationship of the Pliocene rifts of Malta to the Calabrian transform, which brought Calabria off Iberia to its current position. Now, by the Albian, this process seems to be over. Probably this whole process, the transform, the spreading seems to be over, and we return to this northwest-southeast trend, which characterizes most of Africa, in fact. So these rifts are generally older down through here, through southern Egypt at that time. The best controlled ones, and the ones that really show the model for passive rifting associated with the transform, are these Cretaceous ones in Central Africa. Now, they appear to start in earliest Cretaceous times with this Marajo Basin of Egypt, and also as a seed point here, actually in the Jurassic in Egypt, in Sudan, and eventually they won't actually join up until this area in the Aptian. They get going to the Aptian, but at that stage, there is a continuous transfer through. At some stage, they also get driven by the opening of the rifts of the opening of the South Atlantic that we mentioned earlier. Again, these rifts coming oblique to the transforms are of multiple ages. There's at least 3 phases with relatively dormant phases, what are called post-rift phases, in between. And they're not necessarily, they don't necessarily move in harmony with each other. By the time we get to the Eocene, there's only these Niger rifts going, for instance, which with much less rifting in some of the other ones in Chad, but these Sudanese ones are still going rifting at these times. And in fact, the Eocene and Oligocene rifting is quite significant in isolated ones of these basins. It seems to indicate that only certain transforms are moving at that time. Very low, no significant rift shoulders indicated, and very little volcanism. So these rifts are very different. Very different to the classic active rifts, which are shown here for the history of the East African rift system. Really, again, these Sudan rifts are merging into these. The first ones with a north-south trajectory are of Oligocene age in the South Lokichar Basin, and in the late Oligocene and Miocene, these spread out, propagate slightly southwards and northwards, not terribly far, to what I call the Ears 1 phase of rifting. In the mid-Miocene, everything seems to change. The rifts relatively shut down and actually can jump to other locations, such as the South Lokichar Rift moves to Lake Turkana at that time. And then things really start going into what I call the Ears 2 phase, when they propagate further in these 2 directions. For the western banks, there's a lot of volcanism, the purple associated with that. We also kick off in the mid-Miocene, we kick off Albertine, and gradually, I think the rifts propagate southwards. Lake Malawi is largely Pliocene, perhaps around 7 million years old from the onshore geology we know, and we know from there, and from projections of sedimentation rates. And since then, since the Pliocene, it's now kicked off a large branch going southwestwards using old Permian rifts sometimes, and that, Ian Mike Daly believes, is perhaps going to lead to the separation of what he calls the sand plate from the African plate. And indeed, we may also be separating the Somali plate and the Victoria plate in here by the ongoing activity in these rifts. In fact, the peak activity is Pleistocene on 90% of these rifts. These offshore rifts, I think, are different. They don't show the high rift shoulders, they don't show volcanism. And I think they're probably transtensional, associated with late stage movements on the Davy and sinistral movements on the Davy and sea gap fracture zones. What's causing that, I am not sure at this stage, and I'd really value some ideas on that. Compression, two types. One is what I call shocks to the system, which includes this. Generally, these have been given names, some of which are good and sometimes relatively representative or not representative. This Austrian event actually does seem to be tied to the first Eoalpine events in Austria. How it gets through here, probably gets through Tunisia on the north-south axis onto these transforms in Algeria, which are the main expression of them. But then it does get through to the Niger rifts and then through transforms to what's happening down here on this transform system and the rifting of the South Atlantic. Though in fact, spreading hasn't got here at the time. So I don't doubt that this is the main driving force down here. I think this is the main driving force. Undoubtedly, the main driving force when we get to the Santonian event, which is the most significant shock to the system, I think comes from this area, from the consolidation of Turkey and from the abduction of a lot of ophiolites transmitted down to a transform here. And where we really see strong events is in the Western Desert and Sinai, probably having to come down through a transform to give similar effects down here in the Benue Trough. Perhaps the inversions here are more related to what's happening in the South Atlantic. But this is getting 5,000 kilometers from the origin of the compression. So these stresses are being transmitted over long distances, which seems to indicate there must be a lot more transforms around than we are currently mapping. For instance, how do we get to Santonian inversions in the Mandera-Lug basin? There has to be something coming through here to actually give us that. There's also a lot of more minor shocks to the system, such as this Miocene one, which creates a lot of the traps actually in offshore Israel, and actually this also in this West Aristophanes basin. And that seems to be related, can be tied to large transforms coming down offshore Lebanon, which I think were probably there in the Cretaceous as well, and to the onset of subduction of the Eastern Mediterranean below the Menderes torides of Turkey. Orogenes, there's two, one very old, the Cape Fold Belt, which is related to a peak activity in the Permo-Triassic boundary, formation of a large foreland basin behind it at that time, effects regionally ranging right up to the Cuvette Centrale, which is inversions at that time, probably transmitted through this complex here, of rifts. The Atlas, this is actually a map in the Messinian to early Pliocene. The first activity goes back to the Santonian, though it's fairly minor. And also the Eocene activity seems to be fairly minor as well. We get more significant events in the mid-Miocene as these two European platelets, they are Boron and Kabyles plates, come in and collide. But in fact, the most significant activity seems to be on this time slice of latest Messinian early Pliocene age, with a lot of transform movements being kicked off, which of course are still going, which is why the area is seismically active at this time. But what's maybe happening at that time, going on present day, is the creation of an increasing wedge along this margin here. And it may be that we're actually starting to subduct the Western Mediterranean, which is a much younger ocean than the Eastern Mediterranean. It's of Miocene age. These platelets come across very fast in the early to mid Miocene, drifting off Mallorca to create this Western Mediterranean Ocean. It's possibly starting to subduct below Africa now. Now, I'm not saying much about topography in this talk. I mean, we can see a lot of topography developing, the basin and swell structure. The most significant uplift in the world that's not tied to orogenesis and not tied to volcanism seems to be the South African plateau. And there's been multiple debates over the timing and nature of this uplift. Seems to be agreed now that the first uplifts perhaps were in this area and were probably related to Agulhas fault movements. Moving into the main uplift was probably from then up to Maastrichtian times. So it seems that sedimentation rates shut off very rapidly in this orange basin, which is really perhaps timing the uplift quite well. This seems to be related to a deep-seated mantle anomaly. And it's probably no accident that the peak of kimberlite intrusions is around about Santonian, which is also around the peak of this uplift. What is doubt really is when we move up to the very young interval, late Miocene and Pliocene, that some authors believe that there is a second big uplift following a bevelment in the Eocene and the Oligocene to create a weathered surface, and some believe there wasn't. Now, we do know that there is very active uplift along this margin today from raised beaches and things. We don't know that was the case. There's suggestions in sedimentation rates that there was at least some uplift along here. But because we haven't got much erosion, it's we don't see that uplift in the APTA profiles. So the jury is still out on this model of two periods of uplift in the late Cretaceous and in the late Miocene, Pliocene. And that's one of the remaining uncertainties. This one here, the contribution of mantle tectonics, which we still need a lot more data on. We have some very good profiles of the mantle through East and South Africa, but not over other parts of Africa. So, but the main uncertainty really is that a lot of what I proposed are really hypotheses based on regional data, based on analogs to other parts of Africa at different times. That's particularly true in Northeast Africa, Western Desert, and the model, how it relates to the Eastern Mediterranean. The relationship in offshore, onshore is something we still need to do a lot more work on. But we need a lot more readily available seismic. At the moment, we're going on things that are written in papers but are not illustrated. I've only seen one seismic line that really shows this transform along the Egyptian margin. So that's what I'm saying. These are hypotheses at this stage based on analog. We do need the raw seismic data to really, and we did well data as well to mature this and make these maps and the ideas on them more mature. So, for instance, data from the offshore Gulf of Sirte is key to understanding how one transform turns into another transform. Where are the missing transforms in interior Africa? There must be more in order to transmit stress from Northeast Africa to areas like the Benue Trough and to Mandera Lug Basin. So there's Trans-African lineament is a candidate here, as is the Agadem line of Niger. Probably we need to link the observations from these basins, and again, we need more of them, to potential field studies to really map where the missing transforms are. Revisions are necessary. I mean, we probably know plate tectonic positions to within about 200 kilometers around Africa. There's perhaps more doubt on the Eastern Mediterranean, and particularly on the timing of that. To get more exact fix, we need to do a lot more work on, for instance, backstripping out hyperextension. That will probably lead to looser fits than is shown on many of the current maps. I've talked about other aspects. There's the Western Mediterranean route now subducting. I haven't really talked about the Permian reconstructions, but there's still quite a lot of doubt on that, on what Tethys is doing at that time. And I have talked about perhaps extending the Agulhas back to the Jurassic. And the contribution of paleogeography, the advantage of this sort of work is that we can actually put paleogeography, marry the paleogeography to the plate tectonics, as we've done on that margin. So the conclusions, well, I hope I've illustrated that the African plate presents one of the most favorable regions in the world for the study of extensional tectonics and of basin and continental margin evolution, if not by its nature of its geology, then by the availability of public domain data. But we are in a stage now of being able to get the informal hearsay data, bits of seismic, PowerPoint presentations. We can put together model and hypotheses. We need better data to really put these through peer review to, and particularly on the seismic angle, and to mature these hypotheses. We do seem to be showing that all margins are propagational. So talking of an age for an ocean is a simplification. Usually it's propagating, going in jumps, hitting a transform, stopping there, waiting 3 or 4 million years, then taking another jump to another transform. 45% are rifted margins, and surprisingly, a lot of margins are transform and volcanic margins, particularly in Southern Africa. And how this volcanic margin in South Africa relates to the frequency of volcanism around Southern Africa. How does that relate to the South African plateau? Because most of that volcanism is ultimately mantle derived. That's still an uncertainty. Shocks to the African system are delivered from the Attian onwards. This is related to the change in the rotation of Africa, with it starting to move towards Europe in the Santonian. And these penetrate as far as 5,000 kilometers from the point of origin, which means that we really need to find more of these transforms. The plate has been under extensional stress throughout. Rifts developed in all margins. However, the rifts are of multiple different types, and that makes application of analogs very difficult. Again, the rifts tend to propagate as well, so one rift is not necessarily the same age as another, not necessarily the same type as another. A lot of the rifts are passive rifts associated with transforms. But use of analogs from the best controlled areas, areas like that Central African rift system or the West African margin, applied to other margins, allows multiple hypotheses to develop the origin of some of these more truly basins. And that really summarizes where we are at in the understanding of Africa, with more to come. Thanks very much for listening.